All right, to help us out with our energy balance, we're going to introduce a new concept that you may or may not have seen before, depending on how far along you are in your courses. You probably haven't seen it in chemistry, but maybe you've seen it in thermodynamics if you've already had that class. And that is a specific property. So things like kinetic potential and internal energy are all what we call extensive properties. They are proportional to the quantity of material that we have in the system. A specific quantity is what's called an intensive quantity. So it's going to be an intensive quantity divided by an extensive property. So for example, what we call specific volume. So specific volume is going to be volume per unit mass. And when we represent things with specific properties, they have a little hat or a little caret over the top of them. So instead of having a dot, which is a flow rate, they now have a hat, which represents that it's per unit mass. So this example on the screen shows you volume per unit mass. This could be volume by itself per unit mass, or it could be volumetric flow per unit mass flow. And that's important too, because remember, we could have volumetric flow or mass flow in our systems. So as an example, a specific kinetic energy is something that we could also have. And a specific kinetic energy would be represented by a capital E sub K, but with a little caret or a little hat on top of it. And so that would be something like saying 300 joules per minute divided by 100 kilograms per minute gives us 3 joules per kilogram, which is considered a specific property. So we like specific properties because we're going to see them later when we do balances. And sometimes it's easier to do a specific property than it is to get the flow rate itself. Specific properties are things that could be looked up in tables. There are lots of tables in your textbook that you can find specific properties of specific fluids or things like that going forward. So that's the idea behind a specific property. So notation, right? If it's just a U, it's internal energy. If it's U with that caret over the top, it's specific internal energy, right? So specific internal energy is going to be U divided by M. If we look at U and it has units of joules and mass has a unit of kilograms, then specific internal energy should be joules per kilogram. So many times we're not using this form of the equation, we're using this form of the equation. Because we may have a mass flow and we may be able to look up a specific property in a table, and that can give us the internal energy flow. And that might be what we want or not what we want, depending on the type of problem that we have. So what this is going to allow us to do is move back and forth between specific properties and the actual flow rate itself, or the actual amount of energy itself by using a mass or a mass flow rate going forward. So we care about this because in open system, we have a new term that's called specific enthalpy. And specific enthalpy is defined as the capital letter H. And capital letter H is going to help us solve a couple more problems in a slightly different fashion as we move forward. So that capital H is specific enthalpy, and that is defined as, that's what that triple equal sign means. Specific enthalpy is defined as the internal energy plus the pressure times the specific volume of the system. And so what you'll notice here is this is specific enthalpy, and that P times V we actually saw in the last video, and that is work of a system. So enthalpy is a new term for us to relate internal energy and work to each other, add them together, and we get what's called a specific enthalpy. And remember that 3 equal sign, that triple equal sign that you see there, it means that it's defined in this way. So the last thing that I want to mention is with specific enthalpy, we can have a flow rate of enthalpy, but it's more common that we're going to see a specific enthalpy with the hat on it, and it's a combination of internal energy and work. So for example, a specific enthalpy could be something like a molar flow rate, because we can actually have N instead of M. So with all the specific properties we've just talked about, instead of M, we could have N. It could be a molar specific enthalpy, and that's important. So let's say, for example, we wanted to find the flow of enthalpy in the system. We could take the molar flow rate, multiply it by the joules per mole, which would be the specific molar enthalpy, do a little conversion from moles to kilomoles, and get how many joules per hour are associated with the enthalpy of the system. So enthalpy is a little bit more vague of a term. It takes a little while to kind of wrap your head around it, but the idea is that it's a combination of internal energy and work in a system, and that we're going to see things like specific mass, and we're going to see things like specific moles. So make a note to yourself, because I don't have it really well distributed and shown in these slides, that this M could also be other things. It could be N, it could be other things in the system. So most of the time we'll see moles or mass. And that's going to close us out on specific properties. So make sure that you understand the notation first for specific properties, and that you understand that it could be mass or moles that we're going to use with these specific properties.